Hello everyone. So I am Milan Sil from Indian Center for Space Physics, India, and thank you, the organizer, today for giving me opportunity to present our work on exploring the noble gas species in the radiation-dominated region. Here in radiation-dominated region, I mean the evolved star of basically high mass star like the Crab, a supernova remnant. So I here want to highlight the noble gas molecules like argonium ion, ArOH plus, NeOH plus, and HeOH plus. In this Crab nebula environment, ArOH plus is the first detected noble gas species in this Crab environment by Barlow et al. 2013. And Richardson et al. 2013, they modeled the H2 emitting knots in this Crab filamentary region where the kinetic gas temperature is of the order of 2000 to 3000 Kelvin. And here the H2 basically formed by radiative attachment reaction with high abundant electron react with hydrogen atom, and then again hydrogen anion react with hydrogen atom to form H2 molecule by associative detachment reaction. So later this argonium ion was detected by Shilke et al. 2014 by some continuum sources like Sagittarius B2, W31, W51 by Herschel Hi-Fi instrument. And also Barlow observed these transitions, rotational ground state transitions of ArOH plus by Herschel Spire instrument in this similar environment. So motivating with this work, we aim to study the hydride ions ArOH plus, NeOH plus, and HeOH plus, and as well as the other hydroxyl ions ArOH plus, NeOH plus, HeOH plus in the similar environment. There is another groundbreaking work by Gustin et al. 2019, who observed the first molecule formed in the universe, that is HeOH plus, in the planetary nebula NGC 7027 by Sophia Great instrument using Sophia telescope. They observed the rotational transitions J equal to 1, 0 in this source. So HeOH plus is the first molecular ion formed in the universe because it's a higher ionization potential than hydrogen. They react, He plus ion react with electron, first He atom formed, and then HeOH plus react with a proton. And we first prepare a realistic model for the diffuse ISM because Shilke et al. 2014, they observed this ArOH plus in the diffuse continuum sources. And for this, we used the physical parameters used by Shilke, initial hydrogen abundance 50, and these physical parameters and this initial elemental abundance, and used this spectral energy distribution and find these species like ArOH plus. This black curve shows the ArOH plus density profile, abundance profile. This gives roughly of the order of 10 to the power minus 9 abundance. And you can see here that the diffuse interstellar medium is roughly atomic, where the H atomic abundance is very high, and H2 abundance is increasing with the increasing visual extension. And you can see here the H2 profile is anti-correlate with the ArOH plus. So ArOH plus is used as a tracer in purely atomic cloud region. And we also established from our modeling some specific species, simple species column density. And we compare our modeling results with observation by Indriolo et al. 2012, who observed diffuse cloud toward W51. And our result is well matched with the observation result. And then after reproducing the feature in diffuse interstellar medium with our model, we prepared a realistic model for the Crab. And for that, we used the cloudy spectral synthesis code, and we used plane parallel geometry in a radius 2.5 parsec. And these are the physical parameters and initial elemental abundance used in Wayne and Barlow 2015 paper with their Clumpy model 6. And from radiative transfer model, we see using radix, taking the column density of ArH plus 10 to the power 12 order per square centimeter from Hamilton 2016 paper and line width 5 kilometer per second. From the radiative transfer modeling, we conclude here that actually we used hydrogen atom, hydrogen molecule, and electron as a collision partner, and checked that from here electron density is roughly of the order of 10 to the power 3, 1000 to 3000 1000 to 3000 per cubic centimeter electron density, and temperature roughly of the order of 2700. And H2, the contribution of H2 is negligible when H2 density is below 10 to the power 4 per cubic centimeter. So here, and we used a parameter space, and x-axis is the density of H2 and y-axis is the cosmic ray ionization rate. And from this parameter space, we reproduce the surface brightness observed by ArH plus 2 transitions, OH plus 971 gigahertz transition, and H2 2.12 micrometer transitions. Their surface brightness signify these values, and this contour shows these values, and we find here the density roughly of the order of 10 to the power 4 per cubic centimeter, and cosmic ray ionization rate of the order of 10 to the power 7 reproduces our model with observation. And taking the best fitted model, we check the simple species abundance and simple ions and temperature roughly of the order of 10 to the power 3 to 4 temperature in this crab environment. And here we check the abundance variations of ArH plus, NeH plus, and HeH plus, and compared with the OH plus abundance, which was observed by Barlow 2013, and also checked some hydroxyl ions noble gas. And here we calculate emissivity for the crab, and here you can see that the observed prominent transitions of OH plus 308 micrometer transitions is comparable with the 36 ArH plus 21 and 10 transitions from our emissivity plot. And these are some emissivity.
2 minutes left, yeah? 2 minutes left.
Okay. And also we checked the detectability of various transitions of these hydride ions. Here we checked 3 parameters, actually the optical depth calculated from the radiative transfer model radix, and the atmospheric transmission, and also the surface brightness from our model, and compare with the OH plus surface brightness of these transitions, and concluded some possible future detections using a space-based telescope. And also we calculate quantum chemically using Gaussian software that some rotational constant of the hydroxyl ions of noble gases, and also give the catalog files which are not available in the CDMS or JPL database. So these are my summary, and I want to acknowledge our group by Dr. Ankon Das, and also our collaborator, and especially Professor Paola Caselli, for our collaboration in this work. And thank you for your kind attention.